Hi there. My name's Professor Register, and today we're going to introduce you to BioCalculus. This is more of an introductory video to introduce you to what BioCalculus is all about. I'm teaching at American River College, and this is for Math 355 and 356, as they are currently numbered. Previously, it was 350 and 351. To begin with, this is one of my favorite courses or course sequences. BioCalculus is really a catch-all for a number of different classes. We're going to give you an accelerated look at calculus as well as other higher mathematics topics, but it's all going to be related to biology and medicine. And that's really the big picture of what this course is all about. Before we jump into an example, let me just give you the briefest of introductions into what to expect in this course. And so to begin with, let's start with just this simple model, the Kermack-McKendrick SIR model. This is how you model pandemics. And so when you're thinking about the most recent pandemic, this is the simplest model that we can use to model it. There are much more complex models, but this is the basics, and this is really the fundamental structure of all of the other models out there. Notice we have dsdt equals negative beta si, didt equals beta si minus gamma I, and then drdt equals gamma times I. This is a system of differential equations, and the goal of this course is to help you understand these. We want you to be able to understand this model. We want you to be able to understand why it includes all of these terms and what the derivatives represent. And we want you to be able to build models like this, as well as more complex models of Kermack-McKendrick or SIR models or any type of model out there. In order to do this, there is a lot that needs to be done. If you look, this is the list of topics that we have in BioCalculus. We don't get to this point until we're really at the systems of ODEs and chaos theory. This is an example of a system of ordinary differential equations. To get there, we're actually going to go through a number of topics, beginning with limits and continuity. Limits and continuity and differentiation are really the heart of Calculus 1. It's all about introducing how do we define closeness, and then how do we define rates of change. Turns out everything can be modeled based on how it moves, grows, or otherwise changes. And that's what differentiation is all about. It's all about how do we actually measure that. Integration gives us a way to solve problems which have differentiation involved. Often it's called the antiderivative. Differential equations then takes these ideas and says, well, we can create equations which have derivatives in them. And so an equation which has a derivative in it is considered a differential equation. And in order to solve them, you need integration. Vectors and matrices then is really unrelated to all of the prior topics. What vectors and matrices are, though, is they are a way of understanding higher dimensions. And we're not talking necessarily about physical dimensions. In space, you're not going to be dealing with 7 dimensions or something. But when you start talking about populations, you could certainly have more populations. In this case, we have 3 different populations, the susceptible, the infected, and the recovered. But you could certainly add additional populations down here. And some systems are going to have 16 or more populations. In order to model that information, we need vectors and matrices. Multivariable calculus then takes these first 3, limits and continuity, differentiation, and integration, and introduces how to do them in higher dimensions. So when you are dealing with multiple populations, how do you do calculus? And then finally, systems of ordinary differential equations and chaos theory takes these previous 3 topics and kind of glues them together. And so systems of ordinary differential equations, in order to do this, we're going to need to have vectors and matrices to understand how to handle the systems of them, how to handle more than one equation. But ultimately, it's just a bunch of differential equations. In order to understand their structure, though, we really need to understand multivariable calculus. This would traditionally be done across many, many courses. Calculus 1, then Calculus 2 for the integration, then the course Differential Equations for differential equations. Linear algebra focuses on vectors and matrices. Multivariable calculus is usually done in Calculus 3. And then systems of ODEs and chaos theory is usually an upper division math class. And so the BioCalculus series, which we do in 2 calculuses, is really covering 6 different courses. We are going to be doing it in a very accelerated pace, though, like extremely accelerated. That said, in making it accelerated, we are going to be cutting a lot of material that you would typically see in a traditional calculus differential equations linear algebra series. We're going to be focusing on the parts which are important for biology and medicine. And the applications we're going to be exploring are also primarily going to be focused on biology and medicine. And so cutting a lot of that material out is going to allow us to speed through all of these topics. Really, though, I recommend you treat this course as though it is an accelerated calculus course, because we are going to be going at a very accelerated pace. With that in mind, though, I do want to show you one document, which I kind of view as the heart and soul of this course. So let me share the screen again. And let me show you this document here. It's an old research paper, a mathematical tumor model with immune resistance and drug therapy, an optimal control approach. What this is really a document which is showing the ways that you can model things like chemotherapy. And what's interesting about it is it actually touches on all of these different topics which we just discussed. This is from 2000, and so at this point, it's a little more than 20 years ago, but it gives us a good foundation for looking at the different types of topics that we're going to be looking at. And so it begins just by introducing some of the fundamentals of tumors and how they grow, but then it goes into some graphs like this. This is something which you would see in multivariable calculus. These are graphs in 3 dimensions, and we'll learn how to graph in 3 dimensions once we get to chapter 9. It then continues to show what happens when we have different types of equilibria. When we're talking about tumors, ideally, we want to have an equilibrium where there is no tumor. That's kind of the goal. And this type of a graph is a chaos theory graph. Whenever we're exploring equilibria and how things can change with regards to equilibria, that's chaos theory. The idea being that depending on your initial conditions, you could end up with no equilibria, 1 equilibria, 2 equilibria, and the stability of them will also change depending on your initial conditions. From there, though, we start talking about a model, and they develop a model for tumor growth. It is dependent on 3 different variables. And let's see if I can zoom in here real quick, maybe using the zoom button. And so we have I of t represents the number of immune cells at time t. Big T of t is the number of tumor cells, and N of t is the number of normal or host cells. Well, our goal is to try and develop a model, and we can see that they start discussing some terms, such as this one. The presence of tumor cells stimulates the immune response, which is modeled by this growth rate. So this is the growth term, rho I of t, t of t over alpha t of t, which is probably a Hill equation or something. But then down here, we can see the actual model. And so it's I dot, which represents the rate of change of the population of immune cells, is equal to S plus this term minus this term minus this term. Then we have T dot, which is the rate of change of the population of tumor cells, is equal to this. And then N dot is equal to the rate of change of the number of normal cells. Now, one of the goals for this course is to be able to understand everything that is going on in this equation. And it's something which is very doable. Probably by the time we get to differential equations, we'll be able to understand a model like this, and we might be able to develop a similar model to this. These terms, I mean, the equations themselves look complicated, but they're not once you start to break them down. For instance, in this case, the rate of change of immune cells is equal to S, and so there is something which is constantly providing immune cells into the system, plus this term, which is talking about the interaction of immune cells and tumor cells. And so when immune cells and tumor cells interact, it causes an immune response, which boosts the rate of immune cells. And so the immune cells are going to increase in number when there are immune cells interacting with tumor cells. That said, immune cells and tumor cells, when they interact, is also going to have a negative effect on the population. And so the interaction is going to cause a decrease in the number of immune cells. And then there's a natural death of immune cells. And so immune cells will naturally die even if there are no tumor cells. For the rate of change of tumor cells, we have this first term right here, R1 of t times 1 minus B1 of t, which is our logistic growth curve. And so this is the standard logistic growth term, which is going to represent an increase up to some carrying capacity. We then have this term here, which has the interaction of immune cells and tumor cells. When immune cells and tumor cells interact with one another, it has a negative response on the growth rate of tumor cells. So the number of tumor cells is going to die off. There's also this term, which is kind of a little interesting. This is tumor cells and normal cells. And so when tumor cells and normal cells are interacting, it has a negative effect on the population of tumor cells. This is probably a term which comes from competition. And so when you have tumor cells and natural cells vying for similar resources or whatnot, there's going to be a limit on them. And so if you have a ton of tumor cells and a ton of normal cells, there's going to be issues. And so it's going to have a negative effect on the number of tumor cells. For our third one, the rate of change of normal cells, well, again, we have this logistic growth term. And then we have this term, which is the interaction of tumor cells and normal cells has a negative effect on the number of normal cells. And so that's this model. And by the end of this course, you should be able to understand that without me explaining it all. But they go a step further. And so now they introduce a drug into the system. And so we assume that the drug kills all type of cells, but the kill rate differs for each cells. And they have an equation which represents the fraction of kills. Well, when you introduce this drug into the system, we have this new system, which is really the same old system, but now it has this term here, the A1, 1 minus e to the negative u I. And so this is the u of t is representing the amount of drug at the tumor site, essentially. And this term, for the first one, you can see that it is having a negative effect on the population of immune cells. For the second one, it's having a negative effect on the population of tumor cells. The third one, it's having a negative effect on the population of normal cells. Well, a question might be, why would we want to introduce a drug into the system which is going to kill off immune cells and normal cells? Well, that's what chemotherapy is all about. The goal is to try and find a steady equilibrium, a tumor-free equilibrium if we can. And so we want to kill off the cells until we've gotten rid of the tumor. Once the tumor is gone, then we'll have just the immune and normal cells. And so the rest of this document is saying, well, how can we explore what a stable equilibrium would look like? And in order to do that, there's a lot of math that goes into play. And so again, here's a look at the stability and instability. This is chaos theory, where we're modeling when things are stable and unstable. But then they start to talk about null surfaces. Null surfaces are where we're going to get things which are zero. And so rates of change which are equal to zero. And so when is the rate of change of immune cells going to be zero? When is the rate of change of normal cells going to be 0? When is the rate of change of tumor cells going to be equal to 0? If we can figure out a point where all 3 of them are equal to 0, then that is considered an equilibrium. Well, once we have the equations for when each of those is equal to 0, we can determine whether or not that equilibrium is stable or not. In order to do that, we start by using matrices. And so matrices are the standard notation for representing larger populations. And here's an example of how we might do that. Notice we have I dot, T dot, and N dot. Each of those corresponds to the rate of change. And so the rate of change of I, the rate of change of T, the rate of change of N. And this is a way using matrix multiplication to write these different equations out. And so they've now got 3 equations written in this structure. This is called the linearization around the equilibrium. It's also known as the Jacobian, I believe. But once we have that, we can calculate something called the eigenvalues. If all of the eigenvalues are negative, then that tells us that we have a stable equilibrium. Well, it turns out 2 of them are guaranteed to always be negative. The third one is not. And so the question is, when is this third one going to be negative? And we have an equation for it. The equation is tied to the resistance coefficient. And so that's how the tumor cells are going to resist the drug. But it's also tied to how much of the drug is introduced into the system. And so what this is telling us is that if we can introduce the correct amount of drug into this system, it will cause the tumors to stop growing. They will be at a steady state. And that's really the goal of chemotherapy. And so this is a mathematical model which shows what is going on with tumor growth when we are introducing drugs into the system. And it uses a little bit of everything that we just discussed. There's also some more, as you go in, we see more derivatives down here, more modeling here, a little bit more graphs. And they go much, much further. Here we have our Jacobian, again, linearization. And there are other solutions, other equilibrium, which we can explore as well. And they do a little bit of all of that. But when we think about what all of this has included, well, it dealt with a lot of differentiation. Differentiation is the study of rates of change. And so how can we measure rates of change of a function? That's what all of that stuff with the dots was. In order to solve things, we would need the integration. We're talking about something which we are assuming is a continuous function. When we think about the number of tumor cells or the number of normal cells, well, we need to be thinking about how this population is. Really, it's going to be discrete numbers, but it's much easier to model using continuity. It was all a bunch of differential equations. When we had that system with 3 differential equations, well, that's what differential equations are. And in order to model it, we needed to have vectors and matrices because it was a system. And we needed to find the eigenvalues, which is a very heavy tool when we're talking about matrices. In order to show the diagrams, we needed multivariable calculus to show things that are happening in 3 dimensions. And then in order to really understand the equilibrium, we needed systems of ODEs and chaos theory. In pretty much any biomedical field that you go into, anything in ecology, medicine, biology, doesn't matter what you're looking at, as well as other fields such as business and economics or physics or anything like that, you're going to have models like this. Everything in the universe can be modeled using systems of differential equations. That's really the bottom line, because everything is moving, growing, or otherwise changing. And that's what systems of ODEs model. In order to understand them, though, we need all of these tools. And that's really the purpose of BioCalculus. BioCalculus is here to give you those tools. On BioCalculus 1, we'll cover this section. BioCalculus 2, we will finish it off. And by the end, the goal is for every single one of you to be an exceptional biomedical researcher. That said, I will let you get started on your homework because I am sure you have quite a bit. Good luck.